This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Approval. I gave a couple of students applied. I gave the approval.
And when we can see the result?
It's not decided by me. So what will happen? I think maybe tomorrow or day after tomorrow they should do it. So what is your name? Your student. What is your email ID? Sorry.
My email?
Anyway, I'll check it. Because I also don't know. Because they will. Yeah, I don't know. Because the committee will be making a decision.
Yeah.
I think I got 10 students email me. I gave all the permission. So the committee will look into it and they will make a decision. Anyway, I'll check it. Yeah.
But my average score is just 78.
Okay.
Not very high.
Yeah, because they don't call me. They don't inform me. I also will see. Yeah, I think they already made a decision. I will check it. Yeah, because they already sent out a mail. I have to check it, whether your name, which one you got it.
Or if I fail this,
Did you apply for some other projects?
just
Yeah, I think that's maybe unfortunate if you don't get it. Because some students will apply for multiple projects.
just apply one.
Yeah, because it's not, I'm not making a decision. I don't have anything. Because the committee will maybe tomorrow. I think tomorrow or day after tomorrow. Definitely they will let you know if you have got. Otherwise, also you can come and do some work, but then it will not be paid. So we can get some good work. We got some good projects. Get in touch with me anyway. Anyway, good. I'm glad that you are thinking. Yeah. Thank you.
Do I know what output looks like? This constant or
I think it's 10 kilohertz.
what it looks like the DC?
So you are getting the 10. I think that's a mistake. I think this is 10 kilometers. Yeah.
This mistake?
So where is other one? See, I think I have provided this one.
Yeah, that's also like this one.
Oh, this is a frequency demodulation.
Yeah.
Yeah.
What the output of
No. So that is a VCO. Actually, it's a VCO. Actually, this is not the VCO output. Because here you are getting the clock 10 kilohertz.
What's output of this one?
So this one is you are getting the demodulator, and the low pass filter output is a demodulator.
Yeah.
And then initially when it starts you may get a DC, but then later you will get 10 kilohertz. Because this is the carrier it will be
But
recording.
there's not a 10 kilohertz.
No. Initially you will be getting a just before this one is coming there is nothing. And then you will be getting a constant DC voltage.
It's constant.
Yeah.
So you means if before weighing input,
Yeah.
it's like this one.
See, if you check here, so this is a 400 audio transmitted, and then this is a FM noise, and so this is a demodulator output. See, this is a demodulator output. Yeah. But then all the pins are not shown here. So this is one pin, they're just simply showing like this. Yeah. And then what will happen is when you have this low pass filter output is this one, but then it will go inside to the VCO, and then actually this is a VCO input actually going to the input of the VCO. It will smoothen.
This is VCO input.
Yeah. So this is a VCO when it is going here, and then this is the demodulator output.
But this is a demodulated output. I think it seems like the input should be.
No. Here I think the confusion. I think that these two slides I will correct it because this here I am using just a PLL block.
Yeah.
In this one, if you want to get analog signal, you have to take from here because here it will be digital. Okay. But then this is fine. This part is fine. But then here I will modify because this is from inside an IC. All the connections are not given.
Yeah.
You know what I meant? So please don't compare this one with this. These two are different. You know what I meant?
So they're different.
Yeah. So I'll modify this one so that I'll remove it and then put another one. Okay. So this is applicable to this one. So what from this one, what you have to understand is when you have a demodulation, you have to take it from the low pass output.
Yeah, low pass output.
Yeah. That's the audio. But yeah, this one I'll correct it anyway. Let me thanks for letting me. I will just remove it.
Okay.
Yeah. Thank you.
PCB soldering on the real PC. It's only practice.
Practice, yeah. Because your PCB did not arrive yet.
And how about the programming stuff?
We will be giving you the program.
But not this week.
No, not this week. Maybe next week we'll give you the program if the PCB did not arrive in time.
Is there any announcement? Because this week is big time.
Yeah, so what we are planning is we will be having some extra sessions. Lab here. Maybe evenings you can come and solder it. And then if you don't finish it, we also got some time after the software, after the exam. Yeah, we give enough time. Okay. So your email ID, what is your email ID?
Sorry?
What is your email ID? I forgot. Because,
Can't hear you.
yeah, email.
Why?
Because we are inviting you for the coffee question. You answered the coffee question, then you also will get an email because you answered one coffee question.
So I just want to confirm you, none of the PCB board has been finished, right?
Still fabricating.
So what we do for tonight, for today's workshop?
You can do soldering practice,
Okay.
or you can collect your components.
Okay, that's
The components we have solved.
Okay. And what about code? Are you gonna teach us or are you gonna?
We will give you the code. We already uploaded code in the but then we will help you in the sessions.
In the workshop? Or?
In the workshop, yeah.
Okay.
Not this week, next week.
Okay. Maybe
coming
I will
week.
ask the code.
Yeah, sure. So we will start voltage regulators. So I will be discussing PLL again next lecture. Couple of questions. So you please go through the PLL slides, and I will discuss a bit more on PLL. I will also show you a video next time on PLL. So now we will start the voltage regulators. Why? Because I am not showing the video and I am not going to ask you the questions, because you may please go through the slides and get an idea of PLL. Because otherwise if I ask you, you might not be able to answer properly. Maybe some of you might answer, but then I want all of you answering the question. So please go through the PLL slides, and we will discuss some of the important concepts or some of the tricky questions in the next lecture. And I will also show you some questions related to the PLL, and then some video, because video is very important so that you can see how the PLL is locking, because that will give you some more idea how the PLL is capturing the input signal. So voltage regulators. So voltage regulators, before that we will just cover the exam, because exam is coming. So for the exam we will have multiple choice questions. We will have system level questions, including short questions from lecture slides. So system level questions are something like design a system to measure the temperature of this room, something like that, those type questions. And then some questions from the slides. Then there will be questions from DSO. So that is the reason DSO you must understand. So there will be questions from the DSO. So these are 3 sections in your exam. Multiple choice questions, there will be 10 multiple choice questions, and then a couple of system level questions and a couple of DSO questions. So there will be a big DSO question with subsections. and the marks will add up to 110, and then I will take the half. So that is more fair rather than setting it for 27.5 and multiply to 55, because 45% is from your lab, 45, remaining 55 is from the written exam. So what I said is when you have 55, see 45 lab, 55 your exam. In the 55 what I did is I did not set for 25.5, but rather I set it for 110. Then I will take half, because if I take 27.5 I know that it is not fair, because if you are losing half mark then you are losing actually 1 mark. So but other way around is if you are losing 1 mark you are losing only half mark. See, it is more fair. So that is so then you should not be taking it granted. So if you are losing 10 marks you are losing actually 5 marks. So I set it for 110, that is what we do. And then there are some couple of examples. So number of comparators, so the multiple choice, then you might, because you might ask me what type of questions, so that's the reason I included some. Number of comparators in a 4-bit flash ADC. So it is definitely how much? 15 number, 2 raised to 4 minus 1. A student decided to use a cascade of 4 RC passive filters, so 4 poles in a circuit to get resonant frequency FR. What is output voltage at the last stage at FR if the input voltage is V in? Because you got 4 poles, then how much it will attenuate? 1 by root to the whole raised to n. Maybe you have to increase the difficulty of questions since you all are answering. Then you have encountered with the below filter circuit, and there was no document attached explaining both type of the filter and working of the circuit. Your crazy manager asked you to explain the circuit without any simulations but only by inspection. Assume that op amps are ideal. So these are some questions. What is the circuit? Because these are DSO, all the questions are kind of a realistic questions. Nothing philosophical or ideal questions. All are kind of testing your real knowledge in the circuit analysis and system analysis. Even DSO, if you understood DSO pretty well, all the blocks, you will be able to answer the question related to the DSO. So these are examples of some short questions or system level questions. Then one DSO question was very simple, which we asked a couple of years ago. Draw a simplified block level diagram representing DSO project hardware you have designed during this subject, something like that. This some students made a mistake. If you ask, draw. So one thing what you have to do is you go home and then you please try to draw end to end of DSO block. And then visualize, okay, signal is coming, these are the block, each block does what, because that is the best way to prepare for the exam. Yeah, anyway, I will discuss some of the past DSO questions in the coming week so that you know what type of questions we will be asking, because DSO preparation is a bit different. It's easy preparation, bit different type of preparation, because we don't have much to study from the lecture slides. No, this is only a section in the DSO. No, entire block level diagram. No, not the front end. Front end is useless without without the other blocks. The front end everybody will say, because just you need some amplifier, some ADC, so filter. No, the entire block level diagram. So if you wanted, so someone asked the question, when I say draw simplified block level diagram, then it means the entire block level diagram, not the front end. Because front end anyone can draw. Even the invigilator might draw the front end. So the entire block level diagram. So how you should study your DSO is when your DSO is working, you should test each signal point and understand what are the signals at each point, and then you again draw the block level diagram by yourself without looking the block level diagram provided on the LMS and understand how the signal is propagating. Yes.
The DSO block diagram, there's so many pins. So do we need to specify every pin?
No, you don't have to specify every pins. You can, if you say block level diagram, the block level diagram could be as similar as what we represented on the LMS. So we want to see only the major signal, the signal, how the signal is flowing. We don't need to represent all the pins. Yeah, we will tell you in the question. I'll show you some of the questions in the coming lectures. So now onwards, in this second lecture, I will discuss about some questions so that you know how to prepare for DSO and then how to prepare for in general ESD. So power supply. Power supply is generally constructed to provide a ripple-free DC output for either one or many sub-circuits. So we need a power supply, otherwise your system will not work. An ideal power supply provides a constant DC voltage despite changes to the input voltage or load conditions. So this is ideal one. Ideal one means it can draw at any amount of current but voltage will be constant. But the real one means when you are drawing more current, your voltage might drip. So voltage will reduce. So that's the reason in your power supply, when you are using a power supply, you have to check it. Okay, this is 5 volt, and then it will say that maybe 2 amps. So it can provide a maximum 5 volt to 2 amps. But if you try to draw more than 2 amps, what will happen? The voltage will decrease from 5 volt to maybe 4 volt. So there is a limit. So how do you get to DC voltage? So when you can get a regulator on your board, you are using a regulator. The use of the regulator is just varying the voltage. You may have some input 12 volt or 8 volt, but then you need 3.3, you need 5, then you can use a regulator. But then before the regulator, you need the power DC voltage. And then how to get DC voltage? Then you will be converting AC into DC. See, 230 volt AC mains, then you have got a transformer, then the transformer stepping down depending upon your voltage, DC voltage requirement. Then you have got a rectifier. You might have studied a rectifier, bridge rectifier, half wave rectifier. Then after rectification, you will get the cycles. It will convert into AC into DC, then but it is still it is not a good DC. So you need some smoothing. Then you got a regulator. So the regulator part is just for changing the voltage, which voltage you wanted. So the regulator will come here. On your PCB, you have the regulator. But then regulator you have to connect to somewhere, that you are connecting to a power supply. But in a system when you are designing, it will be connecting to output of a smoothing circuit. For example, this is a 230 volt AC mains. This is a transformer. You got an AC mains stepping down. So coil number is more here, coil number is less here. You are stepping down depending upon your DC voltage. Then you have got a rectifier here. Then you got a smoothing capacitor, because here you got more variations. The capacitor will make it smooth. Then you got a regulator. That regulator will generate the required voltage here. So if I draw these signals, it is more clear. So 230 volt, that is 50 to 60 hertz. That is your AC mains. That is going here, and then here again the AC mains voltage is less, going to the bridge rectifier, and then this output is, see, in one direction. Then what will happen is, but then here this output, but then here that is coming here as well, and then what happens is, because you got the capacitor, this variation is smoothened. Why? Because this capacitor will charge. Then when during the leading edge, the capacitor starts charging, but then it will come here. But then when it during the falling edge, the capacitor will discharge, and then that's the reason capacitor discharge. And then before it is zero, again the next phase is coming, is charging. See, you are getting some kind of a smoothening happen. Then here, this regulator will do remaining job. When you have some voltage, some ripples, this voltage regulator will make it smooth and give you the required number, the required voltage range using the regulator. So transformation and rectification. The regulator is generally preceded by either a linear or switching power supply. which converts an AC or DC power source from a common supply voltage to any number of pre-regulated or unconditioned subsystem voltages. So this is AC or switched DC, because you are using a transformer. When you have DC, transformer will not work. So this could be AC or switched DC. And then you can get here some voltage V out, here you can get some voltage V out from one transformer. Then sometimes what happens is you can make a system like this. Here you can get a plus 5 volt, here you can get a 3.3 volt. Then when you want to make, so what do you mean by regulator? So when you want to regulate something, suppose you want to keep your voltage constant. So if you want to keep your voltage constant, so what you will do? The simple way is you can get a Zener diode. So in a simple case, a Zener diode means inefficient and offers poor load regulation but has very low component count and cost. The Zener and resistor can get very hot, typically used for load power less than 200 milliwatt. So whenever we say that we need to regulate something, suppose we say that I want to keep my voltage constant, say 3.3 volt. So in your circuit you want to keep your voltage constant 3.3 volt, but then there could be some current variations, but you want to keep your voltage constant. So the very simple arrangement is something like this. Then what you can do is you can connect your voltage here, whatever the voltage is coming, then your requirement, this could be 5 volt, this could be a 10 volt, whatever it may be, but your requirement is you are getting 3.3 volt, but then here the voltage is different. Then you can connect a resistor here, so the resistor will drop some voltage. Then you can connect a Zener diode, and then if this Zener diode you should buy your required value of interest. If you buy this 3.3, you get 3.3 here, and then you can connect a capacitor here, and then this output is a regulated output, because this Zener will make sure that even if some current is more is coming, then it will flow through the Zener, and this Zener will make the voltage always constant. If Zener is rated for 3.3, here it will be 3.3, even if there is a little bit fluctuation. Why? Because when you have a Zener diode, in the forward bias you got the on voltage, so forward bias, but when it is in the reverse bias, see reverse breakdown, if you are operating Zener in the reverse breakdown, you can see the characteristics. So once we reach here the voltage, then what will happen is, see, this voltage is constant. See, this is the Zener voltage, so it can keep the voltage even if the current is increasing. See, even if the current is increasing, the voltage will be constant. See, the current is increasing. So that's the reason the Zener diode is you can use in the regulator circuit, means it's a simple regulator. So if you want to keep a low expensive regulator, you can use a Zener diode. And then this R is, as I said, this voltage could be some more voltage than 3.3, so remaining you can drop it here. Suppose this may be 7 volt, so this will be 3.3, remaining can be dropped across this resistance. So this arrangement is, this is very good, is low cost, but only thing is that when the current is increasing due to some reason here, when the voltage is increasing here, what will happen? The current through this resistor increases, because when the voltage is increasing, the current through the resistance will increase. That more current is coming, what will happen is the Zener will pass that current. Then what will happen is that Zener is passing more current, but still it is around the same voltage. But then because of that current, the Zener can get hot. That is the only thing. And then this can be used for low power application, 200 milliwatt power watt. So low power, then you can use this Zener diode. Then we usually use in systems not Zener diode. Usually Zener diode is used in some application where we don't need any precision, it's a low power, then we need a Zener diode. But then using Zener diode, there is another problem. Zener diode, you can get the Zener diode, but that voltage, your input voltage will be always more than the output voltage when you are using Zener. But there are situations you need your output voltage more than input voltage. So because of various reasons, we came up with the regulators. So the regulators are linear regulators and switching regulators. So when you read the data sheet, you should be able to know what is a linear regulator, what is a switching regulator, why do we need linear and switching regulators. Under linear regulators there are two types, one is series regulators, another one is shunt regulators, series regulators and shunt. So this is a linear regulator. Under linear regulator we are going to study first the series regulator. So this is a design of a linear regulator, and then this is a series regulator. So why it is called a series? Series means your V in, that is coming in series with V out. See, so that's the reason it's in series regulator. And then how it will work? So the series regulator, you have got one zener. Here also you got a zener, but then you got an op amp, you got a transistor, you got two resistances. So if you have these things, you can make a reasonably good regulator actually. Voltage stepping down, you can't step up, but it's a linear regulator. You can't step up, but you can step down. Step down means if you got here 10 volt, then you can get some voltage, maybe 5, 6, depending upon how you connect these components. What zener voltage, zener diode you are using here. So this is an example. Then we are going to study, so how does this circuit work? So we are going to connect some voltmeters. So when the V input, so here is the load, you are connecting maybe this to a load, maybe this part is going to some load. So when the V in or RL decreases, so when the V in or RL decreases, so what happens? So when the input voltage is decreasing, when the input voltage is decreasing due to some reason, then what will happen?
Across R will reduce because the diode will want to maintain the voltage constant. That acts as reference voltage for the at least there's this split trigger type. So your switch will only be on if your V in and V out are the same.
Yep. So I'll get some values so that it will be more easy. That's correct. So I'm going to design a regulator. So my application is I want to make 10 volt. I'm getting at the input. Yeah, I want to get 5 volt. That's our requirement. Then what I'll do is I'm going to design a regulator. So I got a resistor R1. Then this R1 I got an op amp. And then the op amp. So the negative is coming something like this from here. Again I'm going a zener diode. So the zener diode is represented like this. So this is the D1. And then this output, see this is coming here. A transistor, and so this is your V out. So that's 5 volt. And then from here, two resistances, R2, R3. So this is a regulator. So you got here 10 volt, then you are getting 5 volt. You selected all these values accordingly. So then what will happen? So how can we say that this is a regulator? So whenever somebody says a regulator, if your input voltage is fluctuating, your output should be constant. Otherwise it's not a regulator. The word is, the meaning is regulating something. So if your regulator is good, then if your input voltage is fluctuating, still it will be 5 volt. If your load is fluctuating, still it will be 5 volt. Then how it will work? So if your 10 volt is reducing due to some reason, usually 10 volt will reduce to 9.9, 9.8, that is the range. But I am going just to go into an exaggerated version of 9 volt. So when it is decreasing to 9 volt, what will happen? What are the things happen here? So by the way, before that, so I have designed this, so I have got a 10 volt input, I have to make 5 volt here. So how will I make 5 volt here using this diagram? So I know this is the regulator, and how will I make sure that I get 5 volt there?
So because the gain will be more than 1 in this case.
So maybe, so I am going to select this one as a 2.5 volt. So Zener breakdown. So 2.5 means that Zener will keep that 2.5 voltage that is there. Then what is the voltage? So if I want to get 5 volt here, so if this is 2.5, what is op amp will make sure that this is 2.5 because there is a negative feedback. If this is 2.5 volt, if I select both are same, then how much voltage will get it? Yeah, I get 5 volt. Almost, close to 5 volt. Because this 5 volt into R3 by R2 plus R3. So that is a voltage here. So that's the reason we are getting 5 volt. See how I designed. So these values, so you have to select first a Zener, and then you can choose this R1 and R2. Then you can get the voltage here. That's how we designed it. So this is the case, everything is fine. You got 10 volt, you got 5 volt. Then due to some reason, the case 1, 10 volt reduced it to 9 volt. So if 10 volt reduced it to 9 volt means then here your 10 volt reduced it to 9 volt. Then this is 9 volt, then what are the possibilities? So when 10 volt become 9 volts, what will happen? So when the input decreases, immediately what will happen? So when the input decreases, definitely, because this is the input, when the input decreases, it is connected through the op amp. When the input decreases, input voltage decreases, input current decreases through this R, so that your output voltage definitely will decrease. So when your output voltage is decreasing below 5 volt instantaneously, then what will happen? This voltage will decrease. When this voltage is decreasing, then this is going to the negative. Here you already got 2.5 volt. So this will become less than 2.5 volt immediately. Then what will happen is you are getting more. So your output is V plus minus V negative. So that this error will increase, ER, isn't it? When your error is increasing to the base, when the base current is increasing, what will happen? Your collector current will increase. When your collector current is increasing, then what will happen is this here the more current will be flowing because more current is coming, and then it will again go to the 5 volt. So same way, when your voltage is increasing from 10 volt to maybe 11 volt, when your input voltage is increasing, then your output voltage will increase suddenly, and then this voltage will increase suddenly. But then this voltage is connected to the non-inverting terminal. Then what will happen is the error voltage will decrease, and then what will happen is this current will decrease, and then when this even this voltage, error voltage, you can take it as a voltage, then your VB is decreasing, then what will happen is your current will decrease, so that again you are getting 5 volt. You can discuss, we can explain using voltage or current. So error voltage may be good because here we don't have any resistance connected, so you can use error voltage. So your VB is increasing or decreasing. So that's that one. We got the slide. I have written in the slide so that you can read it later. So V in or RL decreases, here V out attempts to decrease. The feedback voltage, so we call this a feedback voltage, VFB, attempts to increase. Thus compensating for the attempted decrease in V out by increasing the Q1's emitter voltage, changes in V out are exaggerated for illustration. So that's what explained here. So when V in or RL increases, so when V in or RL increases, then the feedback voltage also increases, because then when this voltage is increasing, this voltage will increase. As a result, VB, this voltage B, applied to the base of the control transistor attempts to decrease, because this is going to the negative part, so that this will decrease. Thus compensating for the attempted increase in V out by decreasing the Q1 emitter voltage. So that's how it is working. So in the regulator means you cannot simply use a regulator without adjusting the voltage fluctuations. So if you are making a regulator, you have to make sure that it will compensate for the fluctuations at the input voltage. So that's the reason I have given some example. Easily you can find out. So if this is 18 volt, and then if this is 3.9 volt, so and then you have got 100 kilo ohm here, 47 kilo ohm here, then you can say your output voltage equal to V out, which is equal to 1 plus, accurately 1 plus R2 by R3 into V reference. So which is approximately equal to 12.0 volt. So that's how we will be designing. So we will be designing by choosing the right Zener diode and R2 and R3. So we neglect the drop across the diode, sorry, the transistor. So here we are not taking into account any drop caused by the transistor, because that is a very, very small value. Then there is another problem with this circuit is there is no current protection. Current protection means suppose you are touching this to the ground by mistake, because that can happen in your regulator. Sometimes your output you touch it to the ground, then what will happen? This part you are shorting. When you are shorting this part, what can happen? This will be gone. So you don't have any protection here. So definitely your circuit will damage. So then for that people find out a current limiter. See, they have designed a current limiter. So current limiting. So in the regulator you have a current limiter. That's the reason your ICs, even though when you are touching by mistake your output to the ground, it will not damage. So please don't touch it multiple times, it might damage. But it is your device is regulator is protected for the short circuit. By mistake, if your output is not for you to touch it by mistake, it is in the circuit. If something happens and your output of the regulator is going to the ground touching, it should not damage. So that's the reason you got a current protection in the regulator. So in the current protection or current limiter for series regulator, because series regulator the problem is here your input is in line with the output. So if you are shorting this one, if you don't have a current limiter, what you are doing is you are shorting your emitter to the ground, and then lots of current will be flowing. And so that's the reason you got a protection here. So this is called a current limiter. So current limiter prevents excessive load current. So how it is preventing excessive load current? So if you got a circuit like one resistor and another transistor here, so this is a current limiter. So Q2 will conduct when the current through R4 develops 0.7 volt across Q2's VB. So here this transistor will be only on when this voltage is 0.7, and then that is the limit. So that is a maximum current. So maximum current means this R4, if you connect 1 ohm here, then what will happen is when you have current flowing through this 1 ohm, and if you have 0.7 amps, if you got 0.7 amps flowing, then this voltage will be 0.7, and then when the 0.7 volt is here, then this transistor will be on. So when this transistor will be on, what will happen? This current will be taken by this here, because why this is, when this is on, why this one is taking more current than this one? Because this is the collector. So collector current is this is the base current. So this collector will take lots of current from here, so that you don't have that more current going to that one, so that your current is limited to 0.7 amps. So that's called a short circuit protection. So this short circuit protection, this is an interesting circuit. Even in the op amp, when we studied in the ECD, we studied the main blocks, but then there is one block here near the output. So that is a short circuit protection, see here. So this type of circuit is widely used. That is called a current limiter. So that is made of one resistor and a transistor. So that is used for limiting the current. So maybe I can draw it and show you. So how this circuit is working? So you have got V in, then this is the R1, then this is your regulator, positive, negative, then from here you got your Zener, then you got the feedback, then this is coming to the Yeah, so this is circuit. So here we don't have any short circuit protection. So if you short it, then lots of current will go through, but we need to have some short circuit. So our interest is, I want to define short circuit means then we should be defining, okay, after this current we need some kind of protection. So what is the maximum current you want to draw? After that current you don't want current flowing. So then you will say, I want to have 0.7 amps. So that is the maximum current you are defining. So in that case, what you need is, you need some circuit that should be helping you to make your current is 0.7 amps. So for that, what you will do is, then you will put a resistor here. Then you will connect 1 ohm resistor here. So if you connect 1 ohm resistor, and then what you will do is, from here you connect another transistor. So this is the emitter, then this is the collector. So this is the collector, and then so this is a Q1, so this is a Q2, so this is a C2, this is a B1, C1, E1. So emitter, base, collector of Q1. So this is a C2, this is a B2, and then this is a E2, and then the E2 is connected to here. So if your current is 0.6 amps, then what will happen? So 0.6 amps will go through it, and then here it is 0.6 volt. So this transistor is off. So 0.1 amps Q2 off, 0.2 amps Q2 off. Why? Because 0.1 ohms means you are getting only 0.1 volt, 0.2 amps means 0.2 volt, because this is a 1 ohm. The resistance is equal to 1 ohm. So when it is so and so 0.6 amps, then also Q2 off, because then you are getting only 0.6 volt. But when it is 0.7 amps, then what will happen is 0.7 amps, then Q2 become on. So 0.7 ohm. Why? Because then the voltage between base and the emitter is 0.7. So that this will be on. When this is on, what will happen is your collector current will increase, and then what will happen is it will take away lots of current through this one. So that because this transistor is on, and then you got 0.7 volt, then actually you are limiting the current. So you can't, your maximum current, it is not kind of, after that it's not going, it's not shorting. So it's not drawing a lot of current, because this one is limiting the current, because when this transistor is on, what will happen? When that transistor is on, as I said, from here lots of current will go. Because this is the collector, lots of current will go like this and then come here. So that's how it's protecting this circuit is protecting the direct current flowing from here to the ground. So that's how it is limiting. Then my question is, when this one is on, so you have to answer me now or later. When this one is on, so you are getting 0.7 volt here. When this one is on, that's when you get 0.7 volt here, this one is on. When this one is on, what is the status for Q1? You know my question? So you can think of, because if you think, then only you will understand the current limiter in detail. Otherwise, you know that that's a resistor, you are getting a voltage, but that's not enough. So you have to think a little bit more deeper. So my question is, when the Q2 is on, whether Q1 is on or off. So how many off? How many on? So when it is on, what will happen then? We will start from on. So when you short the emitter, what will happen? It will be drawing more current from where? See, if you don't have this short circuit protection, then when you short here, what will happen? Which current is increasing? You are shorting the emitter. Then from where which current will increase?
If we short the Q1 it's off, because that's is 0 voltage difference.
Sorry?
I mean, if we short the Q2, then Q1 will be off.
No, I am taking off Q2 and R4, then I am going to short this circuit. So here I am shorting V out. So what will happen if I short?
Collector current will increase.
How?
Because the load is increased also. If you short circuit, current through the load should increase. Since load current is increasing, it will call for low base current from the amplifier, and that will cause more collector current and emitter current to flow through Q1.
Yeah, definitely your answer is almost correct, but something is missing. But we studied a transistor. Previously we connected something to the emitter, so that's the reason we didn't have any confusion. But at the moment the emitter is open, and then I'm asking a question. So when I ground the emitter, what will happen? So please think about it, and again another exercise, and then let me know next week. So my answer is the current will definitely increase and it can damage. So that is the reason we are having a short circuit current limiting. So when you put a current limiter, again we have problem. Why? Because when the Q2 is on, you are not able to tell me what is the status of Q1. Why? Because this part is not clear. So that is the reason these two sections are connected. Once you are clear of this part, you will be clear of the current limiter, what will happen. So please explain in the next lecture. So but I explained the basic working principle, but then my question was when the Q2 is on, what will happen to the Q1? But then I know that why that is confusion. Why? Because you don't know what will happen when I ground this one, exactly what is happening. So please think about it, and I will ask you these questions in the next lecture. So current limiter is widely used in the electronic circuits for limiting currents. This is in the operation amplifier. There is a current limiter. That is the reason your op amp is in the operation amplifier there is a current limiter. See, short circuit protection. So whenever they say that there is a short circuit protection, they will be putting a current limiter like this in the operation amplifier, even in some other circuits. So then in the linear regulator there is another one called shunt. So previously it was called series. See, this is a series one. Series. Your V in, V out, both are in series. Now we got a shunt. Shunt means parallel transistor. See, the transistor is parallel here. So previously your input, output, see here, this is your input, this is your output, this is a transistor. That is all are in series. See, it's a series, V in and V out, series through this transistor. So this is a series. But then shunt means we use a transistor. See, this transistor, so this is your input, this is your output, but then you have got a transistor in parallel. So use a parallel transistor for control element. If the output voltage changes, the op amp senses the change and corrects the base on Q1 to follow. So again the same principle. When the input is increasing, then what will happen is this voltage will increase, and then this will increase, and it will go here, and then it will be correcting again. I will explain the working principle. So this is called shunt. So first point is shunt. Shunt means your transistor is connected in parallel. So that's the reason it is called shunt. In the previous case, transistor was in series. A decrease in output voltage causes a decrease in VB and an increase in VC. So this is a kind of connection for a shunt regulator. Although it is less efficient, than a series regulator. So usually shunt regulators are less efficient than series regulator. The shunt regulator has an inherent short circuit protection. So here you don't have any problem with the short circuit. So this is again why this one got an inherent short circuit protection, because you got an R1 here, you got a resistor here, and then so your maximum output it can flow is V in by R1. Even though you are shorting here, the maximum current flow is only V in 1 by R1. So if you can choose a good resistor, then maybe a bit rated, high rated resistor, then you don't have any problem with the short circuit, because this will take into account, because the current flowing is decided by this R1. So that's the reason you need this R1 here. So why if I don't have this R1, what will happen? Definitely you don't get short circuit protection, but you have another issue as well. Why do you need this R1 in this design? Suppose R1 equal to 0, what will happen? Yeah. So your V in and V out are same. You are shorting. So that's the reason in this design, see, you are isolating your V in and V out using only this resistor, and the remaining things you are doing here. So we will explain that one. So that's the reason if you are shorting here, because of this resistance, you don't have much issue, because it will not affect the op amp, it will not affect the your transistor. So these things are not at all affected. So that's the reason here you don't need a current limiter. So but then when we come to, now we will come, see here you are connecting this to the ground, then what will happen is this one nothing will happen, this one nothing will happen, only this resistor will stop the current. If it is 10 volt divided by the resistance, that is the maximum current you can get it here, even if you are shorting. But here if you are shorting, again I am coming back to the question, what will happen? So that is the reason we need a current limiter here, but then you have to draw, maybe because it's drawn like this, bit confusion. So what I would recommend is, why don't you connect transistor here, then you think about it. So I think I will stop it here. Why? Because this part should be clear, then only I can move ahead. So I hope to hear from you by email or in the next lecture. What will happen if I ground here? It's a simple question. So if you can't explain, you don't have to worry. I will take 5 marks off your ECD. How about that? And then after this one, you have to tell me when the Q2 is on, what will happen to the Q1? Because these are some circuits now you should be thinking. Because I don't want to give the explanation, full explanation, so that you also will be thinking and then giving some explanation. So we have got parallel, then we got shunt or parallel. Then we will be discussing how this one is working in the next lecture. Then we will study about the switching regulator, and then that will maybe finish the voltage regulator part. So in the next lecture, I will show you some videos of PLL, then bit more explanation on PLL. Then I would like to hear your answers. So as I said, this week we will be having the practice solder section. Practice solder session. So if you want to practice your soldering, use the kit and practice it. But please collect your components for DSO components this week.
For this circuit, I think without current limit, when we short layout, and the Q1 will burn because the current of Q1.